Welcome. This chapter is going to be about electric charges and fields. And to start with, we're going to be talking about the basic concept of charge and electrostatic forces. So electric charges can either attract or repel things. They'll exert forces between different objects. As you can see here, this is on the left, water flowing down, attracted to the tip of a comb by the electric force. On the right-hand side is a cat that's managed to get itself into a bunch of packing peanuts. And again, there's a static electric charge and static electric force that attracts the peanuts to the fur of the cat. And we'll, throughout this chapter, be able to describe these more in detail and talk about the causes of these effects. So the first thing we're going to talk about is how objects are charged. This is a piece of Borneo amber. And so amber, when it's rubbed with a piece of fur, gains electrons. We'll define all this in more detail, but it gains a unit of charge called an electron, which gives it an overall, what we call a negative charge, therefore charging it. The process looks something like this. You have a piece of amber over here, a piece of fur cloth that you're going to rub it with. They have perhaps positive and negative charges, and we'll define those more in detail. Those are two ways of measuring charges. Positives and negatives cancel out. So if they have the same number of positives and negatives, we say in total they have zero charge, net charge. And so they're balanced. They don't feel a force between them. They won't attract other objects. When we rub them together, charge gets transferred between them. And so now after you rub them, it turns out that there's extra negative charge, extra electrons, as we say, over here that have been moved over from the fur. Since the fur lost some of those negative charges, it has now extra positive charges. So we say there's a net negative charge on the amber, a net positive charge on the piece of fur. So what does that cause? That causes these to feel a force to pull them towards each other, like the cat with the packing peanuts over here, or the stream of water attracted by a force to the comb over there. The two pieces of amber, well, rather, if I did this same process on a second piece of amber, rubbed it with another piece of cloth, and then brought these two close together, this amber and this amber close together, they would repel each other. So two things that are charged similarly, negative in this case, repel. Two things that are charged with opposite signs are going to attract. And similarly, these two pieces of fur, if I brought them near each other, would repel each other as well. So the explanation for this, we've gotten ahead of ourselves a little bit by explaining some of the details, but you need a property that objects can have that can be transferred from one object to another that allows them to exert forces on each other. And this property is called electric charge. And this was discovered at least as early as 500 BC. People knew about charging up pieces of amber like this, and that they could exert forces. There must be, because this force could either attract or repel, unlike gravity, where gravity is always attractive, there's one kind of mass, positive mass. To give a repulsive force, we have to have two possible flavors of charge. So there has to be two charges. We've already said they're going to call them plus and minus, where opposites attract and like charges on objects repel each other. That would explain what would happen if we got our extra piece of fur and cloth here. The cloths would repel each other, or sorry, amber and cloth. The ambers would repel each other, but the amber and cloth would attract each other. The other thing of interest here is, like gravity, these act at a distance rather than contact between objects. So I hold the cloth and the piece of fur apart, and I can measure the force between them. I put two pieces of, amber and cloth, or a piece of fur. They'll attract each other. I put two pieces of amber over here, measure the force between them, and they will repel each other. So it's a force at a distance, unlike a lot of forces you talked about in physics 1, which were contact forces, but like gravity. So there are many ways, once people knew about charge, they wanted to study how to create and store charge in an efficient way. And they discovered through many years of research that you can store charge in a bunch of devices. One that was used early on was the Leyden jar. And this was used in particular by Benjamin Franklin. And you could have a metal rod leading off the top. You could rub that metal rod with something like a piece of silk to transfer charge to it, and the charge would go into the jar and be stored on the metal inside of the jar. We'll talk about conductors later on, which will explain this. But one thing he did with this was he demonstrated his famous flying a kite in a storm experiment, that the electricity or the lightning carried charge just like the electricity he could produce in his lab with one of these Leyden jars. And so he realized that electricity and lightning were the same thing. But because it could flow into this jar, he thought electricity was a fluid. He didn't know what it was really made up of, and that it was an excess of it was a positive charge, and a deficiency of it was a negative charge. So this is where we get the sign convention. The thought it was a fluid, positive fluid flows, and if you are lacking the fluid, you have a deficiency of it in material, you have a negative charge on that material. That's where we get the sign convention from. It turns out this isn't correct, as we'll see. It's actually electrons, which are negatively charged, that typically flow in to create an electric current. And it's not a fluid, it's individual particles. So some other brief facts about charge before we go into more detail in the next video. The unit of charge, like everything, when we define something we want to measure, we have to define a unit. The unit of charge is the Coulomb, C, named after the French physicist Charles-Augustin de Coulomb. Charge is what we call quantized, which you'll see if you go on to 240 in more detail in physics. It's a fancy word meaning that it's not continuous. If we keep subdividing charge, eventually we hit a smallest possible amount of charge we can get. And in discrete objects that we deal with, that is 1 electron worth of charge. All physical objects are going to have a total charge that's going to be an integer multiple of this amount. You can't have any old value, you can have an integer multiple of this. But notice this is a very tiny number, and as we'll see, when we're dealing with macroscopic systems, we usually can ignore the fact that this is a 10 to the minus 19th Coulomb if we're dealing with individual coulombs and even millicoulombs of charge being moved around. It's basically continuous because we're so far off in the decimal places with adding or subtracting an electron. This amount can be negative as well. So you can have positive integer multiples of this for positive charge and negative integer multiples for negative charge. The other thing to note is that charge is conserved, which means that the total charge in an isolated system remains constant. If charge can't enter or leave a system, the total charge when we add up all charges present is not going to change over time, no matter what's going on inside of the system. Charges can cancel, and we saw this with the amber being charged before, and that is if we add up all of the charges on the object, some will be positive, some will be negative, the signs are going to cancel each other out. So you can have a lot of electrons in an object and a lot of positive charges from the protons in an object. When you add up all positive and negative, it could come out to 0, and you'll say the object has 0 net charge, even though charges are living inside of it. And it's generally going to be the total charge or net charge that we're going to be worried about. The one caveat to that is that if you go to particle physics, which we're not going to do in this class, charges can actually destroy each other. You can take a positive electron called a positron, an electron, collide them into each other, and the charges will be destroyed. They'll emit photons which have no charge. It still satisfies this, though. The original system has 1 plus and 1 minus charge, which is 0 net charge. The final system, after they destroy each other, has no charge at all, no charges at all, and still 0 net charge. So net charge is still conserved in that case.